Time feels like the most ordinary thing in the world. Every day, we watch the sun rise and set. Clocks move forward in steady rhythm. Seconds become minutes, minutes become years, and life seemed to unfold along a single universal timeline. For most of human history, people believed time was absolute, the same everywhere, for everyone, no matter where you stood in the universe. Time was thought of as an invisible background, flowing equally for all observers. The past was fixed, the present was immediate, and the future was waiting ahead. But modern physics has revealed something astonishing. Time is not fixed. It is not universal. It can stretch, slow down, and behave differently depending on where you are and how fast you are moving. This idea sounds impossible at first because we experience time as constant in everyday life. Our brains are built to assume that time passes the same for everyone, yet the universe operates under deeper rules. In the early 20th century, Albert Einstein introduced a theory of relativity, and it became one of the most mind-bending truths ever discovered. Space and time are woven together into a single fabric called space-time. Space is not separate from time. They are intertwined dimensions of one reality. And this fabric is not rigid. It bends. It curves. And when it bends, time itself changes. Imagine two identical clocks. One remains on Earth. The other travels into space at incredible speed. When the traveling clock returns, it will not match the one left behind. It will have ticked more slowly. The traveler will have experienced less time. This is not science fiction. This is real. Experiments have confirmed it again and again. The faster you move through space, the slower you move through time. This effect is called time dilation. At speeds close to the speed of light, time slows dramatically. If you could travel fast enough, years could pass on Earth, while only days pass for you. This is why astronauts aboard the International Space Station age slightly more slowly than people on the surface. The difference is tiny, only fractions of a second, but it is measurable. Time itself is flexible, and the universe proves it. Even particles and accelerators, moving near light speed, survive longer than they should because their internal clocks slow down. Muons created in Earth's atmosphere should decay before reaching the ground. Yet many survive because time moves differently for them at high speeds. The cosmos is full of evidence that time is not a single universal flow. Relativity forces us to abandon the comforting idea of one shared clock for the entire universe. Each observer experiences their own passage of time depending on motion. This leads to the famous twin paradox, where one twin travels near light speed and returns younger than the twin who stayed behind. The paradox is not a contradiction. It is a demonstration that time is not absolute. The universe does not grant a single timeline. It grants many, each shaped by movement. But speed is only one part of the story. Gravity also changes time. And this is where space becomes even stranger, because time is not only affected by motion, but also by the presence of mass itself. The deeper we look, the more we realize that time is not a background. It is part of the structure of reality. Einstein's relativity tells us that gravity is not just a force pulling objects downward. Gravity is the curvature of space-time itself. Massive objects, planets, stars, black holes, warp the fabric of space-time around them. And when space-time curves, time flows at different rates. The stronger the gravity, the slower time moves. This means that time passes slightly faster at the top of a mountain than at sea level. because gravity is weaker farther from Earth's center. Again, the effect is extremely small in everyday life, but it is real. Scientists have measured it with ultra-precise atomic clocks separated by only a few centimeters. Even the difference between your feet and your head is enough to create a tiny difference in the flow of time. In fact, modern GPS satellites must constantly correct for time dilation. Their clocks tick differently because they are moving quickly and because they experience weaker gravity than we do on the ground. Without these corrections, GPS navigation would drift by kilometers every day. Time dilation is not just theory. It is part of the technology we rely on. Now imagine what happens near something far more extreme, like a neutron star or a black hole. Near a neutron star, gravity is so intense that time slows significantly compared to distant space. A minute near its surface might correspond to much longer far away. Near a black hole, gravity becomes so extreme that time slows almost to a stop. To an outside observer, an object falling toward the event horizon would appear to freeze. Its time stretched endlessly. The light from it would fade and redshift, as if it were trapped in slow motion. But for the falling object itself, time continues normally, at least until it reaches regions where physics breaks down. This creates one of the deepest mysteries in science. Time behaves differently depending on where you stand. The universe does not provide a single shared clock. Each observer carries their own flow of time, and this leads to a profound realization. Time is not the same everywhere. The past, present, and future are not as simple as we imagine. Space is not just a stage where events unfold. Space and time shape each other. The cosmos is a dynamic fabric, and we are moving through it constantly. The deeper we explore the universe, the more we discover that reality is far stranger than human intuition. Time is not a river flowing the same for all. It is a dimension that bends, stretches, and changes with motion and gravity. And beyond relativity lies an even deeper mystery. How does time behave in the quantum world? What happens at the center of a black hole where gravity and quantum mechanics collide? Does time have a beginning? Did time start the Big Bang? Or is time an illusion created by the way we perceive change? These questions remain unanswered, but what relativity has shown us is already extraordinary. Time is not fixed. It is not universal. It is shaped by the universe itself. In the vastness of space, time becomes elastic, warped by speed and gravity, reminding us that reality is far more flexible than our everyday experience suggests. The universe is not only vast in distance, but vast in the strange ways it reshapes the fundamental flow of existence.